Bull and make it through the rest of the class? Maybe I'll get Ann to cater us some Red Bull when we go through the statistics in the hard math sections. We might need the extra, right? I did try to make the statistics part a little easier and not go over it in so much detail, so I hope that worked for you guys. Everybody ready to get started? Got our cookie and everything securely munched, our apple. All these little boxes, lunches are exactly the same. After 5 or 10 years of it, you can kind of predict reliably what's in the box. Anyway, let's go ahead and get started. We talked about T1. This is the time it takes to make an HTTP connection to the server that's going to answer your request. T2 is the time that it takes to send that server a request and get the first byte back. We talked about that a little bit. We talked about why T2 isn't constant. We talked about why T2 is 0 most of the time. And I think people might have been surprised about that until they gave it some thought and realized that most HTTP requests were for static assets, not a whole lot of server thinking necessary. Now we're going to talk about T3, which is the TCP transport time. This is by far the most complex of the time segments. And I could easily go on for hours and hours and hours. There's textbooks out there about TCP IP and how it works. I'm not going to trouble you with all of that, right? You get one slide, maybe two, but no textbooks on this. Very interesting topic. Most of the action that happens in an HTTP request and response happens here. It's the network transport that's actually interesting. The rest of it is not all that interesting. Making a connection, DNS lookups and whatnot, not that interesting. Anyway, the TCP transport time, T3, basically, we've made our connection. We're going to transport this object. TCP has rules about how it does this. It ramps up the amount of data that it's sending according to some special rules, and then it gets to a maximum bandwidth, and then it stops and plateaus. And if the file is big enough, it'll carry on like that for a while, and then it'll stop. TCP IP is designed very well for large files. Unfortunately, on the web, does anybody have an idea of what the average size of an object, what the distribution of sizes of objects on the web looks like? So let's see. I'll pick on you. What do you think the average size in bytes or kilobytes of an object on the web, just across all the different objects?
4K.
Oh, man. All right, so I fed him that answer beforehand. Really, I did. No, the average on the web is between 4 and 5K. Right? Tiny little objects. TCP IP does not work well for small objects. Right? Sort of like an airplane. Right? The airplane doesn't work very well when you're just warming up, moving 10 feet, and then landing again. Right? Now, if you're going to Europe, it works fine. But firing the jet up just to go 10 feet and land again, not worthwhile. That's what you're doing with TCP. You've got a huge mechanism for moving large volumes of data very quickly, but you don't really have large volumes of data to move. No wonder it's not very efficient, right? And the whole point about web performance is that HTTP doesn't use TCP efficiently. That's the bottom line. How do we make HTTP use TCP more efficiently? That is the fundamental performance problem. And we're going to talk a little bit about that. HTTP2 itself is designed to do exactly this. All it's designed to do is improve bandwidth efficiency. Once again, remember, HTTP or HTTP2 either can't make any packet arrive more quickly than it would have any other way. Right? HTTP doesn't know beans about packets. Right? It knows about messages, requests, and responses. Right? So when we talk about TCP, what we're really talking about is how do we efficiently move a whole bunch of small objects over a system that was designed to transport small numbers of very large objects. Right? And this is what we call the head of line problem. So TCP is basically a closed system. There's an equation that describes how things get loaded into it. And the equation for a single object And remember that it doesn't matter which HTTP version we use for a single object, right? Is this first one here for a single object? I've written it there. And it's in the standard networking textbook. Anybody seen Kuros and Ross? Principles of Networking Networking Architecture or something like this? It's a standard textbook in networking. So the solution is in there. Don't take my word for it. Go ahead and look it up in the textbook. So he solves it for a single object. And in one of the problems in the textbook, I think he gives you the problem of solving it for multiple objects. It's not very different. Nobody cares. But that was all written back when HTTP was still using what we call version 1.0, and every object had to be transported by itself. You create a connection, open it, pour the data down, and close it. Next object, open, pour, close. Right? Sequential, very slow process. We upgraded to HTTP 1.1, which gave us keep alive. We now have persistent connections. More than that, we have multiple parallel persistent connections, right? Which is the name of our model. But before that, we only had single objects. And Kuros or Ross or one of these guys in the textbook solved that equation. When we first got HTTP 1.1, a guy named Menashe set out to solve that same equation for HTTP 1.1, and he did for a single object. Boy, that was helpful. Right? I mean, it's like that was not very useful. But the proof was in the book, and you can go and look it up. And so, disclaimer here, the moi went and solved and published the actual final state equation for HTTP 1.1, which you see here in 2009, and I was the first person to find that solution to this equation, and nobody else has managed to find a solution or even bothered. The number of people who actually managed to look at it is probably only 3 or 4 to begin with, so it's not a big deal. But this is the equation that actually solves this, and what it says is that, you know, for one base HTML page with M objects on it, each one has so many bits, right? You have some fixed bandwidth over your line. So many connections per host, and in unique host names, you can turn the crank, put the numbers in, and up to the point of a few idle times, you can tell how long it's going to take that web page to go over the line. Do you think it works? Yeah, I was asking this guy sitting next to you, do you think that works?
I would assume it does.
Huh?
I would assume it does.
So it works up to a point. Now, nowhere here in that equation or any of these other equations do we see anything that has to do with HTTP. It's all about TCP, isn't it? Right? So with this equation, I can solve TCP problems, but I can't really say anything about HTTP, right? So as long as I'm only dealing with TCP, it all works. And boy, I can solve this well within the 5% margin of error, and people will just look at me cross-eyed when I just run the numbers, and boy, I get a real good data out of it. There's just one problem, which is that we're talking about TCP here, and HTTP is really the problem, and it doesn't appear anywhere in this equation, right? So we have this problem called head-of-line blocking, which means that if you have a whole bunch of requests going out over a connection, and just like the freeway again, remember the freeway analogy we used earlier, right? So your small object is sitting behind some big truck, right? Maybe a movie, maybe some big flash file or something in that queue. And that file is going to take 10 times as long to shove out as the next object, right? Now this is inefficient, right? You've got things waiting while other things are loading. You've got a wait state, right? This is what we call head-of-line blocking. And basically what it means is that the big guys are in the same line as the small ones and nobody gets a good deal. If you set it up so that you have a truck lane and the small car lane, everybody will be able to use the freeway more efficiently, right? This is basically the idea behind HTTP 2. In HTTP 1, that doesn't happen. We have head-of-line blocking problems. This equation falls short. And that's why I never published anything further on my model, was because I was never able to get past the head-of-line blocking problem. I reached a closed solution for MPPC, but I wasn't able to make it go any further. Now, when we get to HTTP 2, our life is going to be much simpler. But for the moment, I just want to make a couple points here about the current situation on the ground rather than dreaming about the next version. A couple points here. K connections per host. What the heck does that mean? So here's my web page, and it's got a bunch of HTML tags in it, and it starts HTML, you know, head, close head, body, end body, and it's got a bunch of stuff in it, and in there references URIs to other objects, right? Transitive or intransitive hyperlinks. So by definition, the browser does something a little bit crazy. It sets a constant for itself, and it says, this browser can only make so many connections onto any given host. And we call this the browser connection constant. And it's usually somewhere between 4 and 6, right? I think the Firefox guys settled on 6. The actual HTTP spec itself says 2, which is obviously incorrect. I think current implementations of IE use 4. At one point, the Chrome guys were opening up an individual connection for each object all at once. In the very early versions of Chrome, they tried to do this. It was an experimental browser. They can fiddle with it. Of course, it brought everything to its knees, right? Did not work. The reason browsers have a browser connection constant is because if you open 1,000 connections onto another host, well, I mean, seriously, if your ISP was going to let you open a T1 line, they would have let you do that, right? It's not going to work. Right? Every browser has a browser connection constant. It says you can open 4 connections to Akamai, no more, right? And that limits how fast you can transport the data, right? It's just, think about it as the number of lanes on the freeway, right? If I make the browser connection constant 6, now I have 6 lines on the freeway, right? And I can move traffic more quickly. Usually the value of the browser connection constant is between 4 and 6. I think Steve Souders actually set it to 128 once and brought his machine to its knees. It was a fun experiment. I actually went through and tried to change this value in order to increase the equation. I knew I couldn't do anything about this. It's set by the browser, so I tried modifying this, and that didn't help either. That's what we call domain sharding. Right? And once again, it's a dumb idea. If your ISP was going to let you open a T1 line onto your browser, they would have done it, right? Important point, the browser lets you open so many connections per host. And when we say per host, what we mean is unique host name on the page. So here's my page once again. I've got links to Akamai, I've got links to DoubleClick, I've got links to one of the counters. Give me a good name of one of the folks that do counting, Baynote, right? So I've got each one of those as a unique host name in my page, right? So maybe I have 4 unique host names other than the base page. So I've got, the CDN, I've got the ad, I've got the counting mechanism, and I've got, something else, right? 4 unique host names. I can open 4 connections per unique host name. I can now open 16 total connections to drag data down for that web page, right? If the amount of data on that web page exceeds how much I can pour down those 4 connections or those 6, then those things wait. They block and they wait. And this is what we see in wait states. And this very, very clearly happens when we go to do waterfall diagrams later. We're going to go to a web page. Actually, I think we'll go to Yahoo just because it's a good example. They have a lot of crap on the page. And I worked on that page, so I'm not being critical. We all knew there's a lot of crap on that page. When we go there, we'll immediately see that when Firefox goes and loads the base page for Yahoo, the first thing it does, go open 6 connections to Akamai and start hauling stuff down like crazy. And we'll see that stuff queues, waiting to come down over that connection, and is in a wait state. If we went and calculated this equation, remember I talked about the head of line blocking problem, right? So that only applies to the base page. I don't have any head of line blocking at the CDN. Each one of those is an individual connection, right? Think about our multi-phase process. We get the base page, we get the intransitive hyperlinks, right, the static stuff, and then we do our deferred loading cycle, ads and counters. In that first cycle, T3, unlike T2, is not terribly important, right? The time that it takes that base page to come back, the time between the first and last byte arrival of the base page, usually not that large. I mean, how big can that base page be? right? Base page is over 100K of text. I mean, that's a lot of text, man. It's like, you know, I don't think my book is going to be 100K in text, right? It's actually a little bit more, but text compresses well, and you know, the base page object is not very large. The TCP time to take Yahoo's base page, index.html at www.yahoo.com, from their server down to my client, very, very small part of the E to E, right? So back to our phases. First phase, we get the base page. Second phase, we get the static content. Third phase, we do the deferred loading. Let's ask ourselves from the point of view of the model, what's important at each one of those stages? In that first stage where you're loading the base page, T1 is absolutely important, right? Because the user is sitting there with no visual feedback, nothing, right? They're sitting there waiting for that base page to come back. The server duration is really important there, right? Because it depends, that determines when you get that first byte back, right? The transport time, which is the difference between the first and last byte, right, is not very much. I mean, that page is not very large. It's just a little text blob, right? T3 is not important for phase 1, right? Now, when we look at phase 2, let's ask ourselves what's important. T1's always important, right? It's always equally important for any given connection. Server duration for the CDN, nothing. We're static flat files, minimal server duration. But the TCP transport time makes up a huge part of it, right? So now we're starting to see at each phase in the loading cycle what's important, what's not, right? If you want to optimize something, optimize the way your base page loads. Don't optimize how the stuff downloads out of the CDN, right? Work it out. We'll go through and look at the actual values for T1, T2, T3, T4 and real world values and show exactly how to do this. But I want you to get into your heads that at different parts of the loading cycle, different things are important, right? The network is not that important in some places, in other parts it's absolutely crucial. And knowing what's important during which part of the cycle is how you solve performance problems. It really is. So T3, this is how we get stuff over the wire. For the moment, we're going to stick with that equation. It'll get us pretty much 90% of the answer, minus a few head of line blocking errors. All right, so this is the hardest one to talk about, T4. So this is what the browser does. And in our model, you remember earlier I talked about the fact that the network is really a seesaw, right? There's a user at one end and a server at the other, and then some connection between them, right? And that connection and how it works is often very complicated. But the think time on the client side and the server think time occupy some finite part of the E to E, and everything else is, you know, network and mechanics, right? T4 encapsulates the user's think time. This includes not just the user think time. Obviously, the browser has to physically do stuff, and we're going to talk about painting and so on the screen. But T4 also includes you as a processor, because you receive some information via optical link, maybe audio link in some cases, depending on which page you go to, but mostly, you know, via optical link, right? And you, that particular client, had to do something with that data, right? You looked at the cool cat picture, right? You read the Facebook update, you know, checked your email, whatever it was that you did. There's think time on your side as well, and that's part of T4. The server's think time is T2, the client's think time is T4, T1 and T3 are just about the network and getting these things hooked together. So the reason that T4 is complicated is because the way browsers work is really complicated. When I first put this slide together, the browsers weren't as complicated as they are now. Now they're twice as complicated. And I've got browsers out there doing, you know, predictive DNS lookups and trying to anticipate what the user's going to do next and prefetching stuff. And, you know, lots of complication, all of it done purely to make things faster, right? Improve performance. But what I want to get across to you is that this is the most complicated part of this. If you look at the hardware and software involved in the whole end-to-end for the web servers are not that complicated. right? I mean, it stats a file to the socket, right? Now, what goes on behind the web server could be reasonably complicated, but just in the web part of it, the browser and the client are by far the most complex parts. Web servers are not terribly complex. The network itself is not terribly complex. You're complicated, and so is the browser, right? So this is also very complicated. Another thing that makes T4 hard to measure and deal with is, God, what's happening on that user's machine, right? I mean, if I'm checking my email and nothing else is happening on my machine, I'm going to have a lot different experience than if I'm, running BitTorrent over here and I'm checking my email over here and I've got an Amazon video running and I've got a stereo running in the background and maybe, my screensaver is back there doing video things or whatever, right? The circumstances, the local network circumstances and local machine environment are highly variable for users. What's going on your machine at home right now? Probably nothing. Or maybe not, right? I mean, back home right now, my machines are like cranking away doing all kinds of crazy stuff. But yours may be sitting there dull and bored. You don't know. And if you measure somebody's performance from, this guy's desktop, and he's back there running, BitTorrent or whatever, then he's going to get a lot different results than he does later in the day, even though nothing else has changed. So T4 is tough. T4 is hard. And the fact that there are a bunch of browsers, and nobody's going to tell you how they work, I mean, at least with Chrome and Firefox, we can go look at the code and pretend that we know how things work, right? We don't really. And, with IE, it's absolutely non-transparent. We don't know how these things work. And it's very complex, right? If you've seen any analysis on first screen paint, anybody seen some analysis on what happens when the browser does its first screen paint? So there's an analysis out there, somebody did it for Chrome and what actually happens. It's very complicated. I was surprised at just how complicated it is, and I sort of pretend to do this for a living. Either way, the way that we set up and measure T4 is there's a specific amount of time that's required for the browser just to do its thing, right? And the browser reads the base page, goes through and grabs the intransitive hyperlinks, throws them into a linked list. As far as I can tell, every browser uses a linked list algorithm for this. I don't exactly know why. Maybe just because it's the simplest. Makes a linked list of those links and goes and starts grabbing them as fast as it possibly can from the CDN, right? And it tries, or wherever it's going, it's not necessarily the CDN. And it tries to do that as fast as possible. In the diagram here, I marked the offset times for parsing the individual objects from the different connections. And I made a little note to myself to talk about this. T4 is especially significant for mobile devices. And I shouldn't really have to make a note for myself because that seems pretty obvious, right? I mean, your mobile browser just doesn't have the firepower that Chrome does on your desktop, right? It just doesn't. The hardware just doesn't support it. So we'll get to the significance of T4 for mobile devices in a minute. For the moment, I'm going to introduce you to your first waterfall diagram, for those who've never seen one. How many people looked at waterfalls before? All right, excellent. All right, so it's not your first waterfall diagram except for a few folks. So you know what's going on here. Every line corresponds to an object on the page. The second line, not the first one, the big blue bar there at the top is just a summary, ignore that. But the first bar there is the base page. And then as soon as we grab the base page, then we start downloading a bunch of stuff. And you can look over here and see what all it is. It's just stuff from Yahoo's CDN. And we'll create your own waterfall diagram later today. I'm just trying to get a pointer here. So that first purple arrow there is the connection that's made to get the base page. This is T1 for the base page, right? We're going out and we're doing a DNS lookup and we're doing the TCP connection. There's no SSL here. And that bar, that first red bar there is the base page. And you can see that it's red and some stuff happens and then the browser starts madly downloading these things. And you can see that these things happen pretty much at the same time. I mean, those four arrows there pretty much all start and end at the same time, right?
Is that time to the first byte that's received, or the entire content?
So this is the entire E to E for each object, and the color codes indicate the different time segments. So page download time total is that blue line. SSL is green, DNS is yellow, orange, depending. First byte time is blue. So for this, at this point, the first byte time ended here, right? And then the last byte time ended there, right? So the TCP T3 is marked in red or brown, if you like. So basically the way that this corresponds, and this is from CompuWare Gomez, and you know, they're not using my model explicitly, although they certainly know about it, since I can't shut up about it if they're in the room. But you can basically see here that T1 is the yellow and the green. There's an orange here for the TCP connect time. But if you look, you can see that in every case, the TCP connect time is very small, and we get these little thin orange lines, right? That's because, like I said earlier, TCP connections are just not a big deal. So one question I like to ask people when we're looking at waterfall diagrams, and I like to stand back here so I can see, it's kind of cricks my neck to get over there. So I'll do this a little bit later on another waterfall diagram, but let me just ask you a question. So what color is it on the internet today? So what's the dominant color in the waterfall diagram?
Red.
Red. So what's red? Let's go back here to our little key and see what's going on. Red. Content time. That's T3, isn't it? The time that it takes the data to come over the wire. So it looks like in this particular case, the largest percentage of the time spent in the E to E was spent transporting the data from the server down to the client. And that's pretty reasonable, right? That's more or less what I expect. If I showed you this with an HTTPS connection rather than an HTTP connection, remembering that SSL is green, what color do you think it would be on the internet? We'll see a waterfall just like that later, right? And you'll see that the SSL times dominate. What I want you to do is develop a skill for instantly looking at the waterfall and say, what color is it on the internet today, right? What is the dominant time segment involved in this page load, right? And here it's the TCP transport time. That's not bad. And you can see that the only place, there's some places here where it looks like the server was working hard. Remember, blue is T2, right? The server duration. You have to wonder, why is there why server activity for, you know, what are commonly static objects, right? And if you look, you say, oh, they are static objects. I mean, hell, that's a GIF. How much processing time does it take, right? Obviously, something got queued somewhere, right? The only reason that the server duration for a static object takes a long time on the server is if it's queued. The server itself does no work statting a file, very, very little, right? So if you see long server durations for static objects, you know that that object is sitting in a queue, blocked and waiting, and it's a distinct indication to you to go look at the capacity on your servers. So if the color on the internet today is blue, what do? Go add some servers, right? Now, I mean, you don't just look at a waterfall and say, oh, it's blue, I'm gonna go add some servers, right? You go and do the analysis. But spot analysis and understanding our model, you can immediately look at the waterfall and say, what's my problem, right? What's the long pole in the performance of my web page, right? So I've tried to point out here some cases where we have time offsets. So these are where connections are being formed. You can see it's sort of labeled over here. They give each connection a connection ID that actually corresponds to what happens inside the client. And you can see that for the most part, once the browser opens those 4 connections, right, it starts downloading that stuff as fast as possible. The waterfall itself is pretty much flat, which is what we want, all the way up to here, and then we start seeing, you know, some time offsets. But for those first 10, 12 loads from the CDN there, Yahoo acted just about as best as they could act. Got stuff there about as fast as they could get it. It wasn't until you got to about here that we started seeing some problems, and even then it's not bad. Back to our multi-phase loading process. Remember, there's 3 phases to loading a web page. We load the base page, we load the intransitive hyperlinks, then we load the deferred content, right? So we can see that very clearly here in the waterfall. We loaded the base page, which embarrassingly enough took 8 seconds, right? This is our phase 1. We downloaded the base page, parse it into a DOM, grab the links for all this stuff. We get to here, roughly. Maybe this one actually goes out to here. And then our phase 2 loads. We do not see the deferred loading here. But if there was some deferred loading, and you typically will when we go do a waterfall for Yahoo later today with webpagetest.org, we'll see there's deferred loading, and you'll see that third set of content, or that third phase in the loading cycle. That's okay. Should I just shout? I mean, like I said.
For the cameras.
Oh, okay. Like I said, nobody's ever accused me of being a wallflower to begin with. So if there was some deferred loading here, we would see it. And we'll see that later when we look at a different waterfall, and we'll look at a little more modern page. But it's very clear, first phase, second phase. And they're very clearly divided. Visually, when you look at a waterfall, you should be able to immediately say, bing, there's phase 1, bing, there's phase 2, bing, there's phase 3. Some of the tools actually mark this. Webpagetest.org puts a line where the phases end, which I thought was nice of them. Anyway, what the browser does is impacted by all kinds of things, right? What if, let's say you get to about here in the cycle and your email client kicks off. And for whatever reason, you know, it's really busy. You got a lot of email going on. It's sucking up cycles and resources on the machine, right? So what's going to happen to the waterfall? Let's just say right here, mail client goes off. What's going to happen? Well, some of those cycles that I would have spent downloading and building this web page are going to go over to starting that mail client, right? And cycles are cycles. If I take them away from this guy and give them to somebody else, this guy slows down. So what I would see if the mail client kicked off here would be a big gap, right? And we see that. And I mean, you can get waterfalls from individual users' machines, and we'll see unexplainable gaps. And it's like, oh yeah, some client started, movie kicked off, email came in, something that disturbed the client when it was doing its processing. And you can see that even here, you can see there's a gap. Why is there a gap there? In a couple other waterfalls we'll look at later, we'll see even larger gaps, and those are actually caused by you in the way you constructed your page. But the client's machine determines how the browser works and how well it works, and there's nothing you can do about that, right? It's like, don't bother trying to optimize that part of things, right? Because it's just not something you can do. I mean, I suppose you could write a piece of malware that went in and shut everything on the user's machine down when you started the browser. That might be a good idea. But user might get slightly annoyed. So knowing everything that we know about T1 and T2 and T3 and T4, very simple. Why did you bother with all this, Daniel? Why did you spend half the day troubling us with all this nonsense? Hopefully there was some use for it. I really hope so. Well, there is. It's right here. Now I can just simply go through and analyze data from one or more websites. In fact, this is an analysis of every website in the top 100 that accepts SSL connections, because when I built it, I was looking at SSL response times. And I broke it down T1, T2, T3, and T4. And Chip, what color is it on the internet? Yeah, what is that? So blue is T1. So do you see what the model's good for? Right? You can immediately, from the back of the room, see exactly what's wrong with the website. right? And you can figure out how to go and fix it. And you can see, remember the goal, right? World-class response time compared to our competitors, right? Well, my competitors are on this bloody slide somewhere, right? Here's B of A and Chase. God help me, some other folks, Wells, right? So how am I doing compared to them? I'm right here. And there's Wells, and there's B of A, and there's Chase. Not doing too well, huh? Okay, so this diagram was taken 2 years, or was done 2 years ago. It's like a famous diagram I used to illustrate this. If I went and do this analysis today with the same tool, this was a tool that I built to analyze this stuff, it's a hell of a lot better. It's not perfect, and we still don't have world-class SSL performance, but it's a lot better than it was.
Is it still blue, or is it mostly rainbow?
So now we've actually started to see, so in this case, in the top diagram, I've broken things down by T1, T2, and T3. I did not include T4 here because I didn't want to include the variability around the user's machine. In the bottom diagram here, I just broke it down further. So this is DNS, TCP connection, SSL, server time, right? So I just broke it down into even further, and you know, it shows essentially the same thing. So ignore that top one and just think about the breakdown here. What color is it on the internet? Still blue.
But that's from 2 years ago?
Yeah.
What's interesting? That's what I'm saying. What is it now, like you're saying?
So in general, the SSL times are down by about 18%. Overall, over the industry. Still, the proportions are not different today, just the numbers. They're still dominated by SSL. And you can see immediately, first thing, you look at that top thing, it's obvious that the response time for every one of these websites is dominated by the time it takes to create the SSL connection. Who knew? I was shocked. I mean, I knew SSL was a big deal. And part of the purpose of the model was so I could quantify that and convince somebody I was right. And I was shocked when I first did this analysis, and I'm like, it can't be that bad. I mean, some of these people are smart.
You know why the PayPal T2 sucks too?
Yes, I do. I know exactly why it does. I know everything about PayPal's performance. Actually, if you want to know why our T2 time sucks, it's because we use CGIs, right? And this is just a legacy from old times when we would love to go back and replace all that, but the transition costs are very high. So that's why our T2 times are very high. And that's our fault. We know that. And we know that we should do better. I accept no responsibility whatsoever for this blue bar. None. Right? I mean, what can I do about SSL? Oh, I can go browbeat my network operators and get them to fix it. I did that. Right? And they did. And it turned out that they weren't the problem. It didn't take them long to fix it because there wasn't much to fix. The real problem was VeriSign and their OCSP lookups, each of which was costing me 600 milliseconds. And I had to do 2 of them because the minimum cert length is 3, and you already have 1 in your browser's root. So you have to make 2 OSP lookups at 600 milliseconds each. 1,200 milliseconds, and I haven't even sent the request yet. Oh my God, it's like my user has left. He's off to Chase and already checked out.
Your competitors are actually a lot better in terms of performance.
What?
Your competitors, such as Chase and B of A.
Yep. Yeah, they're both kicking my butt. Yeah. No, so this was done immediately after I joined PayPal. It was part of my campaign to convince these guys that performance was important. Before I actually came to the company, they had no performance team. Nobody had ever paid any attention to it before. And I started complaining and whining about it. And they're like, you know, don't you have some security to work on or something? And so a lot of the techniques that I'm showing you here were explicitly invented so that I could convince one executive or another, not necessarily at PayPal. I've had my arguments with the execs at Google and Yahoo and Facebook as well, and Sun, right? That I knew what I was talking about. The model makes things really, really clear. If you can get the value of T1, T2, and T3 for your website, and you can do this analysis, immediately you know what to do to go and fix things, don't you? Right? If you're, pick somebody, say you're Comcast, right? So Comcast has decent DNS times, not as good as you would expect from somebody who runs a DNS server of their own, but it is what it is, right? Connection times are pretty good. SSL times are pretty good. Server times are terrible, right? Content times look about similar to the rest of your competitors, but that one is really bad. The only person that even looks like they're close is PayPal, and they're in a completely different line of business. Comcast and PayPal have nothing more to do with each other than oil and water. So if I'm Comcast and I'm looking at this graph, my eye is going to immediately go, bing, what the hell is that? Right? And now I know I have a server duration problem. I know, furthermore, that if I spend money optimizing the server duration, it's going to matter. Right? So here, let's look at Comcast again and look at their TCP connection time. So they've got, and you probably can't read the numbers, I'm sorry about that, but the value here for the connection time for Comcast is, 79.5 milliseconds, 80 milliseconds roughly. Right? So let's say that I don't do this analysis and I think connection times are the cause of my performance problems. So I go optimize that, right? But connection times only make up 10% of the overall E to E, which I can see here, right? And I got 10% improvement out of that. So what does my user get? 1% performance improvement because I optimized the wrong thing, right? And remember that we have to deal with the margin of error. Most of the time our measurements aren't better than plus or minus 5%. Improving something 1% isn't even going to show up in the statistics, right? Don't optimize something that isn't going to get you any result. If you want to optimize something, find the long pole and optimize that. Yes, sir?
How many data points?
So this is about 3 months worth of data. Running tests from, I think we had 28 global locations every 5 minutes. So it's a ton of data, many, many millions of data points. There's a huge, it's a big system, right? It's a big commercial performance management system for a big Silicon Valley company. And honestly, I built the same system maybe 5 or 10 times. I should open source it and just put the code out on GitHub. I should, maybe I'll do that. After you've built something 5 or 6 times, it's just not a big deal anymore, you know what I mean? I hope I didn't break that thing. We're still working. Okay, so this is sort of the money slide in some sense for this class, right? I spent a lot of time getting you through boring statistical stuff and explaining in great detail about DNS and SSL and all these obscure things that really you probably don't care much about. And that whole explanation was to get you to here so that you could see how to figure out what's wrong with your website and go fix it. Does that make sense? Yes, sir.
I mean, Google's homepage is as simple as it gets. And the reason why it's so simple is because the round trip time is truncated because there's hardly any content on there. But these sites, these metrics aren't addressing that.
Right. They're in different business. Right? It's like PayPal is not in the same business as Google. Our pages are never going to be as fast as Google's. I'm okay with that. What I want to have is world-class performance compared to my competitors, right? So when I look up here and I see, oh, Google, yeah, they're beating the crap out of me, no question, right? But what I want to do is make sure that I'm competitive with Wells and I'm competitive with, Chase and B of A, right? And I don't really care, what Google is doing. They're there to, give me a base reference, right? I expect that page to be faster or as fast as any page on the web. And if it's not, I'm going to go and have a few jokes at some of my friends' expense, right? They're super optimizers. It's a good data point, but I'm not in that business. And neither is Comcast, neither are any of these others. These guys were not chosen necessarily because they were in the same business. This isn't a competitive performance comparison. We'll talk about those, measuring your competitors for fun and profit. This was really an SSL comparison. What I wanted to do was demonstrate the magnitude of the SSL problem in comparison to all the other parts of the E to E. And when I look at it, I think I established that pretty clearly. Right? Not just for PayPal, but for every website that takes SSL, the SSL connection time dominates. Right? Who expected that when you connected to, did I leave it on here? Okay, they asked me to remove it, and God help me, the marketing people made me do it. So I had Apple up here at one time, and believe it or not, I gave this class and somebody complained, oh, you're showing Apple data, and so I removed it. But who knew that Apple's SSL connection times dominated their entire E2E for their store? I had no idea. And there was another reason that Apple asked me to remove that. There was a pretty severe bug in the way they were doing SSL, and they didn't realize it until they looked at this. It was an innocent mistake. They thought that by having the high-level SSL cert based in Japan, they'd get better international performance, and it just didn't turn out that way. So when I went and looked at their SSL performance, it turned out that they were actually sending everybody in the US to do OCSP lookups in Japan. And that was another reason they asked me to sort of take it off the slide. They've subsequently fixed that. It's a good example of how even the largest websites with the most competent people can make some pretty harebrained mistakes, right? I mean, the guys at Apple are smart, there's no question. And serious professionals know everything about this. Fat-fingered it, right? Made a mistake, bought the wrong cert and installed it without ever realizing it. And the real problem that they had wasn't that they made the mistake, they fat-fingered it, they put the wrong cert out there. They didn't test it before they launched the product. That was the real problem, and that's our next anti-pattern. It's called bake it in up front. And we'll get there in just a minute, but I'm not done belaboring the T time diagram here. So looking at this, and looking at these sites, right, so you can see how Yahoo works. It's like if you do a secure login, guess what? The SSL dominates, right? WordPress, Wikipedia, all of these people, if you turn on the HTTPS, you're increasing the end-to-end significantly for every single one of them. Does the way to use the model and the model make sense? I really like this slide because it immediately shows you how doing the MPPC analysis immediately shows you what's wrong. Does it make sense?
So I just want to be clear, the DNS connection times are, I thought it was in T1.
Yep, it's in T1. So here's T1. And it's the sum of the DNS time, the connection time, and the SSL time. I just broke it down here because I wanted to convince people that it really was SSL and that the whole web wasn't suffering from DNS-itis or something.
The colors on the bottom don't really correlate to the colors.
No, I probably didn't get the color table, sorry. No, they don't. And I suppose that's why I left the labels there. But it's a good point. I suppose I could go back and make that color table a little better. I need somebody with design skills. You never want some geek to design these things, do you? It never occurred to me to think about making the colors match up between the graphs. And of course, now that you pointed it out, it's kind of obvious. But yeah. Okay, so back to design school. Hey, it gives me something to do, right? No, seriously, does everybody understand the idea? I mean, it's a really basic idea. When I explain the MPPC model to people, they're going, duh, you actually sell that? You know, because it's so obvious and so basic. But until I started talking about it, nobody was trying to do this analysis and figure out what was wrong with their webpage. And if you take anything home, take this technique home. Analyze your website, figure out where the problem is, teach you how to spend your money wisely in terms of the amount of time you spend optimizing stuff. So when the web page loads, remember we had that waterfall, and you could see that the waterfall had these offsets, right, of things being offset from each other, and you know, object A and then object B and object C, and there's some offset. And when we talk about this stuff, what we really talk about when we mean performance is the response time. And this does not have anything to do with packets, once again. It's not about latency, right? Response time is related to bandwidth efficiency. So between myself and my ISP, there's some pipe, right? This is a visualization. There's no real pipe. The internet is not made up of little pipes connecting computers. I've heard people say that, right? But imagine just conceptually that there's a pipe between you and your ISP. And how big that pipe is determines how much data your ISP can send you and how much you can send to your ISP, just like there was water flowing through that pipe. Right? Your intuition about garden hoses will serve you very well talking about bandwidth and latency, because that's where we are now. So between myself and Comcast, there's this nice pipe, and Comcast says it's this big, and I say it's that big, but that's a different topic, right? And given that pipe, how well do I fill that pipe? Is that pipe sitting half empty? If so, then my bandwidth efficiency is very low, right? I'm not using the resources available to me well. And when we talk about head of line blocking, we talk about HTTP efficiency as opposed to TCP efficiency. That's what we mean. We're not filling up that pipe well. TCP itself, ignore HTTP, is designed to fill that pipe to the maximum volume and keep it there until the file is transmitted. And TCP is very, very efficient at this. If you have a large file, no faster way to send it across the wire reliably with, in the correct order, right, than TCP. It works really well. It just doesn't work well for small objects. We get a lot of inefficiencies where we have to block waiting for objects. Remember the big truck in front of the small car that we talked about earlier? We have to block waiting for other things to execute or take place. There's a number of reasons we block. We may just block because we don't have the bandwidth. Either way, we're not using our bandwidth efficiency or our bandwidth available to us in an efficient way. When we talk about bandwidth efficiency, we can calculate this. So the way TCP/IP works, there's really two key numbers, and one of them is the real latency number, and it's packet latency. It's what we call the round trip time. You send one packet to the destination, and one packet comes back, and you measure that time. We call it the round trip time, and then we make some assumptions like every packet that goes to that server is going to experience similar response times. That doesn't actually happen, but we can get an idea of what the time it takes for one packet to go over that wire is, and that's what ping does. If anybody's used the ping utility, it just sends a packet and sees how long it takes to come back. You're measuring the round trip time between yourself and that server. When I'm dealing with HTTP, my round trip time doesn't vary, and neither does my bandwidth. So what does vary? The instructions from the browser on what to load next. And if the browser doesn't do a great job of keeping the pipe full, it won't be efficient, right? So this is actually PayPal, not Yahoo. I try to switch off between my examples so that I annoy everyone equally, right? So this is PayPal, and we're loading the PayPal homepage. And I have deliberately cut off a bunch of stuff like the loading of the base page and whatnot because I want to make a point about bandwidth efficiency here. So this is the section in the waterfall in phase 2 where we're downloading a bunch of stuff from the CDN, right? And since all that's really happening there is some files are being statted and poured over the wire, you might think that it was reasonably efficient, right? Maybe more so than some other parts of the, say, T1 or T3 or T2. So we would like to think that we got good bandwidth efficiency for shared file transport, right? Because that's what we're talking about, right? Phase 2 is just file transport. You got all those GIFs and scripts and so on. But when I went and measured it, and I used a tool called Virtual Round Trip Analyzer from Microsoft. They don't support it anymore because it was the best tool in the business, so they stopped supporting it. I had a few words with them about that. Seriously, it really was. And you can go get the tool. It still works. They just haven't updated it in years. So I went and measured the bandwidth efficiency for PayPal downloading all this stuff. And believe it or not, I got a bandwidth efficiency of a marvelous 1.6%. 98.4% of my bandwidth sitting there doing nothing. I'm not very good at using it. Why was that? Well, all these objects are really small. Only that one long pole object occupied even a few cycles in the TCP stream, right? Everything else used TCP very efficiently. It works very inefficiently for small files. You can see that this is very similar to that. This is just more or less the waterfall turned over, but it's the actual bandwidth, right? So you can see bandwidth used here is about, I don't know, let's eyeball that a little bit, around 2,000 milliseconds. And of course, this long pole corresponds to the red bar there. And you can see that as soon as we hit that red bar, our efficiency goes up. TCP efficiency goes up when the file's bigger. Right? It's just that way. Lots of little files, very inefficient. One big file, very efficient. So when we talk about bandwidth efficiency, we got to keep that in mind. If you have, let's pick some example. Let's say we have Etsy, and then we have Bank of America, right? Which one do you think is going to get greater bandwidth efficiency?
That's because of all the images?
Yeah.
Yeah. So Etsy has all these files, right? And they, compared to the images on the Bank of America page, right, they're pretty large. Yeah. Yeah. What we find when we look around the web is that home pages in particular load very poorly because everybody has tried to optimize them. So they take and they put these little files on there and it's 3 or 4K, for the little file. And they're like, I've run into people that are just so proud of themselves. One guy at PayPal was like, I got the logo so that it would fit into a single packet. Aren't you psyched? And I'm like, look, it's a small file, 1 packet or 5 packets, not going to change the equation much. 10,000 packets, okay, so now we can start getting efficient, right? But by putting lots of little bitty files on our home pages, we're kind of, to some extent. And this is why we do things like sprites, right? Are people familiar with the spriting technique? Basically, we take all the little bitty images and put them onto one big image, right? That big image, much more efficient transport than the small images, right? And spriting is not very different from putting your files into a zip file, is it? Right? Big raster file, zip file, it's a container for some other things. Either way, bandwidth efficiency sucks for small files. So when you're putting your page together, think about that. If you wanted to improve the efficiency of your website, which is about the only thing you can do. I mean, like I said earlier, good luck getting the packets there faster, right? It's like if you can figure out a way to do that, call me, right? Because getting the packets there faster is not easy. Making TCP/IP itself work faster, very, very difficult. Making HTTP work faster, not so hard. HTTP, very inefficient. And that's what HTTP2 and various other optimizations are trying to do. The way we use the web and the way we use HTTP does not work very well with TCP and is very inefficient. This 1.66% bandwidth efficiency, yeah, it looks terrible. And you could say, oh, PayPal, 1.6% efficiency. But let's go measure Facebook. Let's go measure every one of those websites that we looked at in that other graph and see what their bandwidth efficiency is. I did this, of course, and I wasn't able to find anybody who had a bandwidth efficiency above about 9%. Right? Now, somehow, if I can still add, that sort of means that something like 90% of the opportunity to send bytes to the user is not taken advantage of. I'm not doing very well, am I? And it's not just me, it's everybody. And it's the nature of the network and the objects that we put on it. Be that as it may, the important point is that we want to improve bandwidth efficiency. Come to my talk tomorrow, shameless disclaimer, I'm talking tomorrow about HTTP2, right? And how it's going to make the web faster, and literally how, from a technical viewpoint, it's going to make the web faster. And the first thing I'm going to say, and I hope that a lot of the Google guys are in the audience because they're going to stand up and start weeping and wailing and doing the teeth gnashing thing, right? The whole purpose of HTTP2 is to improve bandwidth efficiency. That's it. Right? Every single feature in the protocol designed to increase bandwidth efficiency. No latency. They don't know beans about packets at that level. We do have a problem though. Bandwidth efficiency is great. I love sending large files. I want to give TCP, the opportunity to raise a head of steam and get going. TCP can be really fast if you give it the chance with a large enough file. But I don't often get the opportunity to do that, and I also face a real problem. And that problem is called packet loss. So every now and then, packets get lost, right? This will happen because a router accidentally miswrote one, right? Typoed it. Somehow the numbers got screwed en route, right? These things happen. Packets get lost. If you have a string of 1 million packets, you know, some of them are going to get lost. Typical packet rate loss in today's network for WAN, follow me, for WAN networks, around 1%. This is a big improvement. When I worked at CNET back in the early 90s, and we were putting together news.com, I was trying to figure out why in the world news.com was so slow in India. And I figured it out, packet loss, right? What there really was there was a PPOE tunnel that went under the ocean, and a lot of the packets were getting truncated by the PPOE mechanism. But I was trying to figure that out, and it turned out to be packet loss. That was a huge light bulb for me. I never thought about packet loss before. You know, I mean, I'd heard the stories, oh, packets get lost, and it's like, oh, did you find them yet? And I hadn't got, you know, given it much thought until I had that experience at CNET, and I went back and I learned something about it. Packet loss, a killer. So let's look at what happens to a TCP connection. This is purely HTTP, or purely TCP, no HTTP here. What happens on a TCP connection when you lose a packet? So you lose the packet, the client, oh, I'm sure you know, let me go over it. I know that about half the room probably knows this, right? But so you miss a packet, you got packet 99, you got packet 101, but packet 100 is missing, right? So what do you have to do? When you send the ACK back to the server for those other 2 bytes, you gotta say, oh, hey, packet 100 was missing, you gotta resend, right? That's bad enough. So we have to do a resend, but even worse, TCP cuts your speed limit in half. It quite literally reduces the size of the congestion window, which in TCP terms means how many packets you can send at any given time, by half, right? Every time a packet is lost. And so we get what we call the sawtooth diagram. And you'll see this. Network people will, if you say sawtooth diagram to the network people, they immediately know what you're talking about. What you see is something like this, where bandwidth is here, you lose a packet, goes down by half, you lose a packet, goes down by half, and so on and so forth, right? And via the arithmetic progression, right, it's like that's how TCP/IP works. So if you're at a point where you're sending a file and the TCP is all revved up and it's letting you send, say, a K a second, just to make a number up, right? And then you drop a packet down to half a K a second and you have to start over, right? TCP/IP itself has speed limits built in that limit how fast things can go, and those limits are triggered by packet loss, largely because the people who designed TCP/IP assumed that packets were lost because of congestion. Because in the old days, routers didn't have much in the way of memory. They couldn't do much in the way of store and forward. So when the network got congested in the old days, what happened was the routers would just start throwing packets off, right? And those packets would be lost, then you'd have to go and do a retransmit. That doesn't happen so much today. Routers have gotten considerably better and so forth, but TCP itself is designed so that packet loss is ultimately the limiting factor on the transmission speed. It's not anything else. The only other real limit, and this is a fake limit in the sense that we don't have to impose it on ourselves, is the simple fact that the packet IDs are a 2-bit integer, right, in the packet. So what's the maximum number I can express with 2 bytes? Come on. All right, so the right answer, of course, 65,356, right? And which is, 64K, 2 to the whateverth power, the 14th power, I think. But either way, the reason that this is important from a packet loss perspective is because if the packet IDs only go up from 0 to, 65,355, right? What happens when the packet numbers wrap? Server collapses. No, literally it does. Actually what it does is it throws every packet that's received after the duplicate ID out. Right? So imagine that you're sending so much data that the same packet number occurs twice. What's the server going to do? I mean, TCP/IP depends on packet numbers, right? If you don't have the packet number, data has to be thrown away. If the packet number isn't right, got to be thrown away, right? So what happens is that there's a limitation on how fast TCP/IP can go simply because of the way that we number packets, right? And the fact that when we originally wrote the spec, we used a 2-byte field to specify the packet ID means that we can't have packet IDs greater than, what 2 bytes can hold. And that pretty much sets the speed limit for TCP/IP. Does that seem ridiculous? I mean, the 2-byte choice of that field length, I mean, seriously, it's like we did not choose that field to have some length so that it could keep the internet down. That was not the point of that, right? It's an artifact of an earlier time when 2 bytes was a lot of space and 65,000 was a big number, right? Now it's kind of ridiculous. We do have a mechanism that allows us to change the address space for packets, and basically we put a little flag in there that allows us to express larger numbers, make TCP/IP go a little bit faster. But if that's not working, and it doesn't in most cases, what you'll actually find is that your phone and your iPad actually have completely different numbers for the multiplier in TCP/IP, which makes it impossible to take advantage of that feature, right? So effectively, the iPhone and the iPad are stuck at 65,355 bytes for the congestion window, and that's as fast as these things can go no matter what they're hooked to until they fix that. And they haven't fixed it, and we're on version 7, so I'm not looking forward to the fix. Or holding my breath. The basic idea here, 2 things hold TCP/IP back. 3 things hold TCP/IP back. One is just packet loss. If you lose a packet, the whole thing goes down by half, and you take a sustained loss in bandwidth. The second way is that if you're limited just because you've already got a lot of data in there and you can't have packet number wrapping, right? And the third thing, of course, is if you give TCP/IP tiny files to chew on, right? That's bad for bandwidth efficiency too. But the actual stop signs, things that prevent TCP/IP from going faster, packet loss, packet numbering. If we could fix those, we could solve most of TCP/IP's problems. We wouldn't have to bother screwing around on layer 7 anymore. We're not going to do that. The other point that I wanted to make about bandwidth efficiency is, how do I say this exactly? For mobile devices, so we said earlier that mobile devices have large T1 times compared to WAN connections, right? It just, for various reasons, takes the phone longer to make those connections. If you have to do an SSL connection, obviously the OCSP lookups themselves are going to take longer. Right? Mobile devices are slow, just like SSL is slow. And on that mobile device, bandwidth efficiency is less than half of what it is even on the WAN. So while I got 1.66% efficiency here, PayPal's efficiency on this device, if I go look at my own precious homepage, might be less than 1%. Right? And there's that's not entirely something that I can do something about. It has to do with the way TCP/IP works, has to do with the way the phone works. What I want you to understand is that the key to the whole performance problem is around bandwidth efficiency. This graph and this one are the keys to the whole class. If you can get those ideas, the rest of it is pretty much cut and dried. So I want to make sure everybody's got this part. And in order to do that, I'm going to go through 2 more slides talking about bandwidth and latency. I'm sure most of you guys are familiar with this, but I always find it useful to put this slide up and explain these things so that people can engage their intuition. We've all used a garden hose. We all know how garden hoses work. You turn the knob, the water goes through more quickly. You turn the knob the other way, it goes through less quickly. As long as the hose stays the same size, that's all you can do, right? But what happens if you make the pipe bigger? the hose bigger. Obviously, you can pour more water through. This is the whole idea behind bandwidth. So here in this diagram, this is basically just illustrating the difference between bandwidth and latency because people do confuse them, right? So at the top here, so we're going to transfer a JPEG. And the JPEG is fixed size, no matter how we transfer it. It's, you know, it's my glorious picture, the one I'm going to put on the back of my book. Don't worry, it's not that scary. And I have a big pipe and a little pipe. Actually, I have a little pipe and a big pipe. But when I'm looking at this, for the little pipe, it takes a while to send that JPEG down because it occupies a lot of that pipe and I don't have a lot of capacity, right? If I have a bigger pipe, that same JPEG going to go through the pipe a lot more quickly, right? I mean, this is a very basic and simple understanding bandwidth and latency. Latency is the amount of time it took to ship one byte from one end to the other and back, right? That's my latency, my ping time, my round trip time. My bandwidth is how big that pipe is, and that's up to your ISP, right? Your ISP can choose not to limit your bandwidth, which they won't do, but they could conceivably do it. There are customers that are unmetered customers, right? You can imagine how much the rest of us love those unmetered users since they're drinking our milkshake, right, as far as bandwidth goes. They can sell you a fixed bandwidth rate with a committed data rate. This is typically what most people have. You know, you get a 6 megabit line or a 20 megabit line or whatever it is, right? They can also say that at certain times of the day, the bandwidth is X and Y and Z. And recently, thank you, Supreme Court and FCC, recently we're now able to have the ISPs say, oh, look, you get a bigger pipe than you do because I like the shirt you're wearing. Oh, and the money you gave me, right? And that's called net non-neutrality. And it's very unfair. And it has a lot of technical problems as well. The only good thing about net neutrality is it's unlikely to work, right? I mean, Comcast made a deal with me for a committed data rate. If they don't keep that, by God, I can find another ISP, right? And if they're going to say, oh, you know, I'm going to slow Comcast down so Amazon goes faster, it's like, well, I didn't pay you to do that, neither did Amazon. And Netflix surely didn't. How are you going to resolve those issues? These are contracts I signed, so did Amazon. I really want to see how the Comcast guys do this. And once they figure out those legal issues, I want to see technically how they actually do that. Bandwidth is limited through a process called bandwidth pooling. All the major ISPs use one method for managing your bandwidth. And that bandwidth pooling method does not work very well technically with the idea of trying to manipulate the levers in short periods of time, right? It's not very easy to say, oh, it's noon, turn Comcast up and we'll turn Amazon down. You can't really do that, right? The way bandwidth pooling works requires a long time. This is why we are allowed bursty behavior. You can exceed your CDR from your ISP for some period of time, and then the pooling catches up with you and your bandwidth is limited, right? These techniques that the ISPs use to limit and manage and control and what they do call bandwidth shaping or traffic shaping are blunt instruments, right? The TCP IP network was never intended to have Comcast poking its dirty fingers in there trying to, you know, press the scale down for one person and not for another, right? The system just is not designed to allow that to happen very easily. The ISPs can do this. I mean, as far as I understand it, they're out there doing it now. Technically, it's not a very simple thing, and it has some side effects that other people might be very unhappy about. But I just want to make sure that, given the discussion on bandwidth efficiency, everybody's got the basic ideas. I think I'm going to reorder those slides a little bit. I probably should have put this one first to make sure that the bandwidth efficiency was understood, but I wanted to illustrate the idea of bandwidth efficiency coming off of that discussion around T4. So, what if I make the pipe really big? What if I make the pipe so big it can hold the whole internet? Is it going to make things go faster? So up to a point it does. So I stole this graph from Google and I deliberately did not credit them because they used some data that I helped gather to do it, so I don't feel like I needed to credit them. But be that as it may, the purpose of this diagram is to give you the idea that bandwidth is not the end-all and be-all for web performance. So if I look at this diagram, I can see that my response time and the page load time, response time is what's here on the the vertical axis, right? For 1 megabits, my response time, and I'm just looking at that top graph where bandwidth is changing, right? So it looks like it took 3,000 milliseconds at 1 megabit, right? At 5 megabit, I was down to 1,500 milliseconds, right? So I've just made the pipe bigger, right? Actually, at that point, the pipe is 5 times as big as it was beforehand. I went from 1 Mbps to 5 Mbps. But now when I look at it 10 Mbps, it's not very much different than it was when it was 5 Mbps, right? Looks like I hit a point of diminishing returns around 5 megabits. Does that make sense according to what you're seeing on the graph? Hold that thought just for a second. So it looks like I can only get so much bang for the buck out of increasing bandwidth, and then no matter how much money I spend, if this was 100 megabits, do you think it would make a big difference? What about 1,000 megabits? Is that going to make a big difference? No. Past about 5 megabits, given the way TCP/IP works, everything else being constant, that's pretty much where you flatline and start to hit the point of diminishing returns. It's not very helpful to have 10 megabits. Now, there's fools out there paying Comcast for 105 megabit lines, right? Which are far more expensive than the 70 megabit lines, which are considerably more expensive yet than the 20 megabit lines, all of which are considerably larger than that 5 megabyte window, right? So Comcast is making a lot of money from people who don't understand the system, and nobody has bothered to explain it to them. One of the points that I want to do in my book is explain this so people will stop overpaying Comcast for bandwidth that they can't use. Latency is not a dirty word, even though you might have thought so given the earlier conversation, right? Latency is different. As latency decreases, the response time decreases, and it's pretty much linear. And as long as I keep decreasing latency, the response time will continue to decrease. Now, obviously, there's a lower limit to that, unless we're using, the tachyon protocol or something going backward in time, right? I can't get down to less than 0 latency. And realistically, our computers don't even have clock resolution in most cases below a millisecond, right? That's really for the practical limit, for lower limit for latency, right? So let's say I extend this graph from, we started with 200 milliseconds and we extended out 20 milliseconds, 2 milliseconds, 1 millisecond, right? How much, my latency is going to continue to go down, right? Not as much, obviously. There's just not that much that it can go down. So honestly, there's a point of diminishing returns for latency for practical purposes, isn't there? Right? If you can't distinguish 10 milliseconds, then making something 10 milliseconds faster isn't going to help. Remember earlier we talked about the psychological or the engineering psychology around when web pages are fast enough, right? And at some point, decreasing the latency produces such a small effect in improving the response time that it's no longer worth doing, and we see a point of diminishing returns here. The point of diminishing returns for latency is a little different, right? We're hitting the 0 lower bound, whereas for bandwidth, we never came near hitting any 0 lower bound. It's just the nature of TCP limits it. So when I look at this and I think about my cell phone, right? And I think about the bandwidth that I can get through, the various cell towers and stuff. And I think about what I want to do to make my web pages faster. What's the first thing that comes in mind? When you're thinking about bandwidth and latency, what is it? And I'm just going to pick on you because you're right there. So what are you going to do to make your web page faster? Looking at this.
Reduce the latency.
So you're going to reduce the latency, but it turns out reducing latency is tough, man, and it's expensive, right? So there's only 3 ways to reduce latency, right? So you can reduce the number of messages you send over the wire, right? Which is effectively the same as reducing the number of bytes, right? That's another way. You can reduce the number of bytes coming over the wire. You can move the server and the client closer together, right? And that's it. Those are your 3 possibilities for improving network improvement. Other than that, there are no, there's a 4th one, right? Change the rules of the game, rewrite the protocol, right? But given TCP/IP what it is, you've got 3 choices. Fewer bytes, fewer messages, move the server and the client closer together. right? Those are the things you can do about latency. They're not bandwidth, latency, right? None of those things can be cheap, right? I mean, that part about moving the server closer to the user is definitely not cheap, right? I mean, at Yahoo, we used to have a joke about moving the user closer to the server. It might be cheaper than to move the servers closer to the user. So, fixing latency is tough, and it has a fixed lower limit. If you're in the UK and I'm here in the US, there's a fixed lower limit to the latency, and it's not going to go below that, right? And it's very expensive to improve it, requires changes to the network, requires that, you go pay your ISP some money and say, hey, fix this for me, right? Somebody who writes JavaScript and HTML for a living is not going to be in a position to deal with this, right? Large scale problem to solve. Bandwidth, on the other hand, is cheap and it's easy, right? You call your ISP, hey, I was using a 20 megabit connection. I think I want to try out that 50 megabit connection, right? And ignore the fact that 20 and 50 both exceed the the value of bandwidth. But the point being, bandwidth is easy and cheap to add compared to fixing latency, right? Very difficult, very costly to fix latency. Very easy and cheap, both for you and for your ISP, right, to improve bandwidth. And that's why we have people out there with 105 megabit lines, right? Because Comcast can easily sell you a 105 megabit connection to their servers, not bothering to tell you that the next 100 after the first 5 don't do you much good, right? And you will psychologically feel like you paid them a lot of money, so they owe you something, and your website goes faster now. It doesn't go any faster than if you'd gotten the 5 megabit line or the 10 megabit line. Actually, they tend to threshold it around 496, so there is a slight difference. Yes, sir?
Well, you're talking about these things that they're really bandwidth and latency. But if you increase the bandwidth for everyone, can't that decrease your latency because you're not waiting on other people's packets on a congested line?
So,
Am I misunderstanding something there?
So there's a certain element of truth there, right? So let's think about our pipe again. The picture's gone, sorry, but let's think about our pipe again, right? If there's a lot of traffic flowing through that pipe and your car or your drop of water or your packet now joins that stream, it's got to contend with congestion. It takes longer, and we very clearly see that. If you ping Yahoo at midnight, you'll get a faster result than if you ping Yahoo at noon, or Google or Facebook or anything else, right? So they're not entirely unrelated, right?
So if you're paying them for larger bandwidth and they actually increase the capacity of the pipe, then that could help with the latency.
Then that could help you get closer to the theoretical minimum of the latency, right? So let's say, right, so, and a good example of this is in Ilya Grigory's book, right? In Ilya's book, he goes through and he calculates the speed of light times. And he says, oh, this is how fast things go on the internet. It's like best case for an SSL connection, everything goes fast to the speed of light. And there's no user think time and there's no server duration. So everything goes about as fast as it could go, right? And I deliberately set out in my book to use real numbers, measured stuff, just so that I could show you guys what really happens as opposed to those idealized situations. But I think the way I would phrase what you said is that the greater the available bandwidth, right? So it doesn't really matter how big the pipe is, right? If the pipe is not full, if there's nothing in it, right, then it could be that big, it could be that big, right? And it's not going to make a difference, right? What you're getting at is given all the other traffic that's flowing through the pipe, right? And it's very true when we get on the freeway, right? There's lots of folks on the freeway. Everybody is slowed down. When people get off the freeway, say at the airport, everything speeds up. Haven't you ever noticed how traffic speeds up on the other side of the airport when you're on this side? Right? I mean, this is a fundamental law of physics, right? Airport, slowdown law or something. But really what it is, a queuing problem, right? Because all kinds of people are getting on and off at the airport, right? So because of that, you can actually reduce the latency somewhat, but there's a theoretical minimum set more or less by the speed of light and how long it takes packets to go through cables. Sir?
It's break time anytime we want to go send people across the hall where we had lunch. There is cookies and more beverages.
Excellent, thank you. He saved you guys. No. They're all thanking you, man. They're like, come back in an hour. No. All right, so we will go take a break. But this is an important point, and I'll follow up with you just because you asked that question. And it's this is really important. We will start here next time, and we're going to have a little bit of fun looking at DNS times. So break time, back on your heads. No. All right. Anybody remember that joke?